Please. Thank you. So today we are going to start our discussion on the light sources, and it will start with few fundamental property definitions, and then we'll move on to discuss the relevance in choosing an appropriate light source for particular application. Please remain muted throughout the class. Thank you. So basically, we'll first discuss what is the difference between radiometry and photometry. Okay. So basically, radiometry explores the wider spectrum or wider electromagnetic spectrum, where the emitted energy, the emission and detection both is more in the range from 3 into 10 raised to 11 hertz to 3 into 10 raised to 16 hertz. This is the range in which the radiometry measurement techniques work, where the energy associated with the radiation is considered to be independent of lambda. Okay, so this is the typical range in which the radiometric technique work. On the other hand, photometry deals with the EM spectrum, that is the spectral range, electromagnetic spectral range, that is detectable by human eye, because all these measurement techniques basically started with the ability of human eye in detecting the change in the light properties such as brightness, color, and all as a tools for measurement, right? So the difference between the two are based on the range in which they operate, and the typical human eye range, the sensitivity of human eye changes from 3.61 into 10 raised to 14 hertz to 8.33 into 10 raised to 14 hertz. It is much limited, as you can see, compared to this. And if you, it is you not, we don't talk in terms of frequencies. We usually talk in terms of the wavelength. So this corresponds to 830 nanometer, and this corresponds to 360 nanometer. So this is the range in which we can see that this is a typical visible range. Visible range of electromagnetic spectrum. And the photometric technique work in this. So in our discussion, we'll be discussing mainly about photometric techniques, but for the purpose of comparison, we will be defining the parameters for radiometry as well as photometry and the parallel between them. Now, in the case of photometry, it basically is a science of measurement, because you can see metry, right? It is a science of measurement of light. In fact, when we say light, it is about light properties, whether it is intensity or its polarization or something like that. Now, in especially photometry, it deals with brightness, light brightness that is perceived by our eyes. Means when I say eye, it is always human eyes. Okay, fine. Now, the difference between these two is that, as I mentioned, in the case of radiometry, the quantities which we are going to define are not considered to be function of lambda. On the other hand, the quantities associated with photometry will be considering the dependence on lambda. The reason being that human eyes are not sensitive equally to the to each color. Okay, that we will see in some time, that our eye sensitivity varies with lambda, and that is the reason why the quantities associated with photometric measurement techniques will have the dependence on lambda that we are going to consider. Okay, so in the case typically for human eye, the sensitivity is function of lambda. Okay, sensitivity is function of lambda. It is not sensitive, and it is most sensitive. Can you tell? Can anyone tell it in which range it is most sensitive? Our eyes. Which color it is most sensitive?
Sunlight.
No, it is most sensitive to green yellow color. The in between that. And if you talk in terms specifically in terms of the wavelength, it comes around 555 nanometers. The reason being that our sun has peak energy density emission in this range for this color. Although we see white light when you dissect the light into parts, when we say dispersion, if you consider the contribution of each color, we will see that the peak energy density emission is in this range. Okay, and our eyes are sensitive to this range. It falls in between this range. Okay, it is in between of the visible range, and we'll see that how the sensitivity falls beyond the around this frequency, around this wavelength. Now, it will be interesting to see that we are of course going to study the sensors which are used for optical detection, but a brief discussion on our own sensor eyes will be interesting. That our retina, okay, our retina includes two type of sensors. It is a very sophisticated sensor. Our eyes are very sophisticated sensors, and the two types of sensors are rod type and cone type. They are called as receptors because they are receiving light. They are called as receptors. The cone cells, the cells which are sensitive to light, which are present on retina, they give us the color perception. Which color the object is, it is given by the sensitivity of cone cells, and they actually define the light adapted vision. Means the brighter the object is, these are more sensitive. Okay, and they give us the perception about the object. That's why they define the light adapted version, and it is usually termed as photopic vision. Okay, it is a photopic vision, and they actually lie at the center of retina, central part of retina. And they give the high resolution capability of our eyes also come from cone cells. Okay, now it is interesting to see these cone cells are of three types again. Okay, they are again further divided into three types: red sensitive, green sensitive, and blue sensitive. Right, it is because, can someone tell now? That's why you see your cameras are RGB cameras, isn't it? The reason being that all the color perceptions can be decomposed into these three basic colors, and it comes naturally in our eyes that we have three types of cone cells which are sensitive to red color, green color, and blue color. Okay, now the other type of cells are rod cells. Now the sensitivity of rod cells is more, so they are more sensitive compared to cone cells. But the thing is that they and their spectrum, as you can see, they are more useful for night vision. Why? Because at night we have less light, right? So we need to make sure that we identify the object which is lying in front of us with that small amount of light. That night vision, that high sensitivity is provided by these rod cells, and that type of vision is called as scotopic vision. Okay, scotopic vision. Now, the high sensitivity comes at the cost of low resolution. Okay, so high sensitivity, low resolution, and these cells lie around the so they give us the peripheral vision of the object. So this is a basic about our human eye, where it is governed by the two the cells. One is cone cell, one is rod cells, and they have distinct what you can say, the working of vision, and they provide different information. Okay, now the photometry part. Techniques are based on that. They basically deal with the photopic vision, and since it is less sensitive compared to rod cells, these techniques do not can say spectral sensitivity of human eye, it comes like this. Approximately Gaussian, okay, not exactly Gaussian, approximately Gaussian, and the the, this is a graph for photopic vision. Hello, am I audible? Hello.
Yes, sir, you're audible.
Sorry, actually, my internet got disconnected. Okay, fine. So you can see that here the spectral luminous efficiency function for photopic vision is defined in this form. It is approximately Gaussian, and the peak occurs at 555 nanometers. On the other hand, the dark adapted relative spectral response of the eye, which is called as spectral luminous efficiency function for scopic vision. So I'm not going to write it here, but I will draw it like this. It is similar, but it is a shifted version, and here the peak occurs at 507 nanometers, and this is V dash lambda is for scotopic vision. So both are spectral luminous efficiency functions, but one is for photopic vision, one is for scotopic vision, and the peak occurs for each of them at 555 nanometer and 507 nanometer respectively. Okay, so you can see that our eyes are more sensitive to green color because 32 nanometer is mostly green, but green yellow. Okay, this is more sensitive, and when you go towards red and violet or blue, you will have less sensitivity. Okay, now hello. Okay. So this our photopic vision, as I said, it is less sensitive compared to scotopic vision, this vision is active. It is active when the intensity is greater than 3 candela per meter square. And what is this unit? I will come tell later on. Okay, and for scotopic vision, it is even sensitive to the light intensity per meter square, 0.01 candela per meter square. Okay, so and in between this range, the vision is a combination of photopic and scotopic. So at night, when the intensity is less, this vision is active, and in daylight, when we have good enough intensity available to visualize the object, this vision is active. Okay. Next, we discuss about the quantities and units, because since this is about measurement, we need to understand the different units which are used and different quantities and their units which are used to define the properties of radiations. So first we will discuss about the radiometric quantities, and then later on we'll discuss about photometric quantities, and then we'll discuss that how they are related. So basically the radiometric quantities, let me write. There is a delay in my pen. No. Radiometric quantities. There are number of quantities. So they basically deal with energy content of radiation. On the other hand, the photometric quantities they characterize the response of human eye. Okay. To what? To light and color. When I say light, brightness and color. Okay. In this, when I say that, as I mentioned already, that these radiometric quantities are considering the energy content and the lambda dependence is not considered. Whatever quantities are there, the subscript used is E or no subscript. Okay. And in the case of photometric quantities, in order to define their dependence on lambda, the subscript used is lambda or nu, mostly lambda or nu. Okay. So any quantity with subscript lambda, we should understand it is a photometric quantity. Any quantity which is with subscript E is considered to be should be considered as a radiometric quantity. Okay. So before going into the definition of quantity, we should understand that the light which is being emitted by a light source is going into 3 dimensions, right? And when we consider a point source, then the light will go in all 3 dimensions and typically in a symmetric manner. So we need to define one important term called as solid angle, and it is measured in steradian, right? So how one steradian is defined? It is defined for, let's say that you have a vertex here and you have a sphere. Okay, and if you cut a cone here, On now, imagine this is a three-dimensional surface. Okay, this angle is alpha, and the radius of sphere is r, and the uh, the area here is considered in the definition of your solid angle, that is in the units of steradians. Here, how the steradian is defined is that it is that is having the solid angle is defined where the vertex is at the center of a sphere, and it cuts off an area on the surface of the sphere as I drawn here, which is this area. The shaded area should be equal to the area of a square whose length is equal to the radius. So when I say my radius is r, the square with with length r will have an area of r square, isn't it? Right. So when this area is r square, then this solid angle is considered to be one steradian. Okay, this solid angle is considered to be one steradian. Now consider a simple case where for small solid angles, that means when this alpha is small solid angle, what happens is, if you consider this patch, small patch on a sphere, imagine in 3D figure, a small patch in this thing can be modeled or can be considered approximated with a circle, right? It is not a circle, of course, because of the curvature of the sphere, but considered to be a flat circle. Then for small solid angle, if you can consider the uh, uh, the trigonometric relation with r here, then you will come to know that the circle have the radius r equal to r sine alpha. Okay, r sine alpha, and the area of this circle becomes pi r square. Sorry, so it is pi r square sine square alpha. Okay, now how we have defined the solid angle, that it is the ratio of area, this area divided by the square of this radius, right? So the usual symbol for steradian is this v, which is a function of alpha, this alpha, and it is a ratio pi r square sine square alpha by r square, and r square will get cancelled, and we have pi sine square alpha. This is, of course, valid for small solid angles. Remember that, because only in the case of small solid angles, we can consider this to be a flat circle, okay, of radius pi r square. In the case of radiometry, the first parameter or first quantity which is which need to be defined is the radiant energy, the energy associated with the radiation. And it is expressed with unity with the letter Q, and it is measured in joules. It is measured in joules. Now The next quantity is radiant energy density. And when we say density, it's always associated with the volume. So the unit is joule per meter cube. Okay, so radiant energy Q is defined in terms of joules. Radiant energy density is joule per meter cube. Then the radiant flux, or it is also termed as radiant power. It is radiant power. And what does this define? It defines the time rate of flow of radiant energy. Time rate of flow of radiant energy. When we say time rate of flow of radiant energy is already expressed in joules. So the unit for radiant flux here is joule per second. Okay, and when we know that this is, since it is power, is also expressed in terms of watt. So these are the quantities. Remember, please remember these quantities. These are essential for the further discussion. Radiant power. Now the next quantity which is defined is radiant intensity. Radiant intensity. Now this radiant intensity is associated with the solid angle. Solid angle the source make at a given point in the space. So it is the radiant flux. Now remember, we are not talking in terms of radiant flux. That means we are already talking in terms of joule per second. Radiant flux emitted by a point source per unit solid angle. Okay, per unit solid angle. Now here comes the use of solid angle. Okay, so the intensity is expressed in terms of the radiant flux emitted by a point source by per unit solid angle. Now what will be the unit in this case? So the intensity I is nothing but d phi by d omega, because we have used d omega as a variable for solid angle, and so the ratio of here, what will be the unit? We have already seen that the radiant power, radiant flux or radiant power is expressed in watts, and the solid angle is steradian. So watt per steradian. Okay. Now can you tell me that if phi is the radiant flux emitted by a point source, and if I consider the intensity coming on a sphere, intensity from a sphere, what will be the value of the intensity? Can someone tell? What is the solid angle associated with the sphere? What is the solid angle associated with the sphere?
4 pi.
4 pi. So it will be 5 by 4 pi. watt per steradian. This is per sphere. This is for sphere. Now the next quantity one we need to define is Pointing vector. So it actually defines the direction of propagation of radiant energy, in which direction the energy is propagating. That is defined by the Pointing vector. Okay, remember that. Then comes another quantity, radiant flux density. There is a delay here in the pen. Sorry for this, there is some delay in my electronic pen. Okay, so the next quantity, that is radiant flux density. When we say density here, again the portion of area comes into picture, where we know the radiant flux is measured in watts, and the radiant flux density is measured in watt per meter square. It is the flux emitted from a surface with a surface area of dA, and in that case, let's say d phi is the flux emitted by a surface dA. Then we term radiant flux density, or in this case, particular case, this is called as radiant excitance. Okay, radiant excitance, because it is that radiant energy is exiting from that area, with the area is given by dA. Okay, so d phi by dA, it is measured in terms of watt per meter square. And the now this is about emittance, like the energy is emitted. Now Now the next term is irradiance. Okay, here this is associated with radiant flux density of the radiation that is falling on the surface. Now this is about excitance, right? Exiting the surface with surface area dA. Irradiance deals with radiant flux density of a radiant radiation incident on the surface. And now here, to distinguish between the area emitting and the area on which the radiation is falling, the area here in the case of irradiance, let's say we represent it with dA dash. So the emittance irradiance is expressed as d5 by dA dash. Okay, of course the unit remains similar to radiant flux density at watt per meter square. So this is radiant excitance and this is irradiance. Okay, these are very important terms, especially when we deal with sources, radiation sources. Now the irradiance associated on the surface of the sun associated with sun is 1.37 into 10 raised to 7 watt per meter square. Sorry, 10 raised to 3. So this is the irradiance associated with sun. Okay, and it is a constant, solar constant. Okay, it is a solar constant. Now the when we are dealing with the man-made sources, of course, it is a natural source. But when we deal with man-made sources, one important parameter is the radiant efficiency. Radiant efficiency. And when we talk about efficiency, efficiency is always associated with the input power with the output power, or input energy with the output energy, isn't it? And how that conversion is happening. So it basically describes the ability of the source to convert the consumed electrical power, because most of the light sources are driven with electrical energy. So that how much the supplied electric power is being converted into radiant flux, and that is defined by the radiant efficiency. So with this definition, the radiant efficiency you can express in terms of this is flux divided by the input power, V into I, right? And since both are power quantities, so this is dimensionless, and the values it can take it between yes, the values it can take is 0 to 1. It is a dimensionless quantity, and the values can be 0 to 1, 1 being the highest value, that is 1 efficiency. All the power which is given is being converted into radiant flux, which never happens, right? So in fact, it is interesting to see that the wattage given on your light bulbs, right, it is in terms of watt. So it is not talking about the radiant flux which is being provided by it. It is the power consumed by that. Okay, that we should remember. Okay, now moving ahead, we'll discuss the further quantities and the relationship between them and how they are related. So we have defined what all different quantities we have defined till now. We have defined the solid angle, the radiant energy, radiant flux or radiant power, their units, radiant intensity, Poynting vector, radiant flux density, when the flux is emitted from a surface of area dA, that is called as radiant excitance, and the radiant flux density incident on a surface with a given area, let's say dA dash, and it is called as irradiance. Both are having the same unit, watt per meter square. And remember that in the case of irradiance, it is defined per unit area when the pointing vector is perpendicular to the area, because it may so happen that on a surface where the light uh, is being illuminated, or sorry, radiation is being illuminated, it may not be perpendicular to the surface. It may fall on the surface at certain angle. So that angle will play a role. We'll see to that now. But in the definition of irradiance, it is defined as a radiant flux onto a unit area when it is perpendicular. This area is perpendicular to the pointing vector. And what is pointing vector? It is the direction of propagation, right? Then only this definition is valid. Otherwise, we have to take the area, part of the area which is perpendicular, that we'll see now. Okay. So let's say you have a situation where you have an emitter, radiation emitter of area dA. We have already said it is having area dA, and there is a receiver, let's say, with area dA dash. Now the energy, radiation is being emitted and is being collected by the receiver. So radiation coming from a point on the emitter will have an effect on the entire area. At the same time, each receiver point will receive the radiation in this, right? So here in this case, this angle is considered to be alpha, okay, and the angle made by a point receiver to the given area of the emitter, half angle, is considered to be alpha dash. Okay, and the distance between emitter and receiver is r. Okay, now with the definition of the solid angle, the solid angle is function of alpha, and we know that this area is dA dash and this distance is r, so it is dA dash by r square. Right now, the radiant flux arriving at the receiver is proportional to the solid angle the radiant flux phi, which is arriving at the receiver here, this part dA dash, area dA dash, sorry, area dA dash is proportional to the area of the emitter, because bigger the area, larger will be the radiation which is collected by the receiver, right? So the amount of radiant flux will also be high. At the same time, it also depends on the solid angle. Larger the angle, larger will be the radiation arriving at the receiver, right? So it is proportional to dA and the solid angle. And when we consider it with a proportionality constant L, okay, now what is the unit of this? This is in watts. Here L is a constant of proportionality and it is defined as, very important term, radians. L defines radiance of the source. So L is basically flux per unit area per unit solid angle, right? And what will be the unit? Watt per meter square per steradian. Right? Now, when, as you can see that when the distance between the two emitter and receiver is very large, means they are quite separated. Area dA and dA dash are small compared to R. Then we can apply the same approximation, considering this area to be a small flat circle. Then the flux can be expressed as because we know what is the omega alpha, that is the solid angle, right? We already seen that. So this is the relationship that we get when dA and dA dash are small, very small compared to R. Right? Now, if you look at the radiant flux from the emitter arriving at the receiver, because here what we have calculated, the radiant flux. So this is the radiant flux arriving at the receiver, which is proportional to the area of the emitter and area of the solid angle. Sorry, amount of the solid angle. Now, if you try to calculate the radiant flux from the emitter, here, sorry, from the emitter to the receiver, then it will actually depend on the other quantities, that is dA dash and d omega alpha dash, right? So if you look at that, if you simply look at that, if you look at this definition, L dA d omega alpha, and we already know what is d omega alpha. It is dA dash by R square, isn't it? So if I interchange the position of d and dA dash, we have L dA dash dA by R square, right? Which is nothing but L dA dash d omega alpha dash, right? Now this is the radiant flux from the emitter arriving at the receiver, that is emitted by the the radiant flux coming from the emitter, which is equal to the radiant flux arriving at the receiver. Now this is under the assumption that nothing is lost in between, no absorption, nothing is happening. So, but in practice, there will always be some absorption, so these quantities will not be equal. And this is why we define the radiant efficiency. Right? Previously, we just discussed about radiant efficiency. So, in fact, if you consider the sun, a small example, then we'll close for today. Sun, which is seen from our Earth, and the angle, the small alpha angle which it makes, considering it as a emitter, then that alpha associated, that half angle is around 0.25 degrees. Okay, which comes around 0.004 radians approximately. Okay, so this is 25. Okay, so since this alpha is so small, we can simply replace sine alpha with alpha. That means sine 0.004 radian is approximately 0.004, right? So if you consider the solid angle, it comes out around 6 into 10 raised to 5 minus 5, sorry, steradian. This is d omega, right? And we have just seen that the okay, one more thing I forgot to discuss. One is that we have already seen how phi is defined: d L dA dash d omega alpha dash, isn't it? Now, if you remember that the irradiance which we just previously with letter E, I don't know why there is so much delay here. Yes, so we have already defined E here, as you can see, E as d phi by dA dash, right? That is irradiance. So E dA dash is nothing but d phi, that is phi. You can say this is nothing but phi, that is the flux. So if you replace this L dA dash with E, because we already know that the it is L dA dash is representing. Oh, sorry. L dA dash is representing the uh, irradiance, so it is E into d omega alpha dash, right? So in this case, we have already seen that the uh, so L of sun, that is the radiance of sun, can be calculated based on its irradiance and the solid angle it makes. We have the solid angle it makes is 6 into 10 to minus 5 steradians, and the irradiance which we